Okay, in chat box you are replying. Good. Could you able to see the screen now? See, I could not see the chat box now. You have to reply.
Yes, sir.
Yes. Let us revise the things which we have completed. We are talking about the factors affecting on thermodynamic stability. Total, how many main factors are there? How many are there?
Three.
Right, right. First factor,
Central metal ion.
right, nature of central metal ion. Second factor,
Coordinating group.
coordinating groups or ligands. Third factor,
Ring structure.
right, ring structure or chillet formation. Out of that, the first factor I discussed, and that first factor was also with further 3 points. What was the first point?
Charge on metal ion.
Charge and size, or it is called a charge density. Second point.
Crystal field effect.
Okay, number may be different. Okay, crystal field effect. Yes. Third point. Yes, what was the discussion last time?
Class A and B metal.
Right. Type or category of the metal, whether it belongs to class A or B. Depending upon that and the bonding, stability will vary. These are the points related to the thermodynamic stability. Now, second point I want to discuss today. Nature of coordinating groups or what the ligands. In that, the first point is base strength. Why I am talking about the base strength? Because ligands are, just let me see who wants to come. Vaishnavi. Yes, how we understand the ligands? Ligands are, what ligands do? Ligands are complete lone pair.
Acceptor.
Ligands are lone pair acceptor. Is it right? Yes, give me an example of ligand. Any example of ligand in molecular orbital theory, various complexes you have discussed. This year I am talking about. Last year you have discussed this all basic terminologies as well as various complexes.
Cyanide.
Yes, cyanide
F
or
minus.
carbonyl or arsine
2O.
or phosphine or F minus or generally you can say X minus, H2O, NH3. See, nepheloxetic effect you have studied, electrochemical series you have studied, their strength of ligands you arrange. All these are ligands. What is their speciality? What ligand remain with? Ligand remains with lone pair. And that lone pair is what? That you have to complete.
Donate electrons.
Right, here answer is they are lone pair donors. Any species if donate the lone pair gives the lone pair to that we say as base. It's a base of acid base theory. Lewis acid base concept. As per Lewis concept, ligands which are lone pair donors are bases. Shruti wants to enter. Therefore, I'm talking about the base strength. What's their ability? Because everybody's ability to donate the lone pair will be different. So as their ability varies, the base strength varies. And this is general point. It's not a very perfect point. Higher the base strength or more the base strength or larger the base strength, more will be the stability. Because we're talking about the thermodynamic stability. So it is a thermodynamic rough concept about what the stability. Of course, category of the metal depends. But in general sense, broadly, stronger the ligand, more will be the stability. That we say. Stronger the ligand means what? It is a stronger Lewis base. Why it is a Lewis base? Because it donates the lone pair. Therefore, we say it is a strong Lewis base. Now, for example, if I consider a carbon as an donor atom, I'm saying the ligands for that are cyanide and carbonyl. If I say nitrogen as a donor, ligands can be NH3, NO or NO2 minus nitrite. If I consider oxygen as a donor, then ligand can be aqua group or water H2O or hydroxide group hydroxo OH minus or oxalato C2O4 minus 2 or you can say carbonate CO3 minus 2. Likewise, various examples for the donor atoms and ligands we can what provide. And conclusion is higher the basic strength, higher the Lewis basicity, more will be the stability for the complex. It is a conclusion. Is it clear what I am saying? If no, then say no.
Yes, sir.
One additional point you have to keep along with this, that is,
सर
yes,
रेकॉर्डिंग चालू नाही केली.
actually recording started. What happens? Google platform previously I was using for recording. No, it's a good thing you did, reminding you did. From yesterday what happened? College was with the subscription for that Google, and that subscription was in such a way that recording we could do, that we were getting on the Google Drive, that recording. But now what Google has done, time being it is stopped. After renewing, it may start. But what I am doing, I am recording, screen recording. Even you also can do the screen recording. Many apps are there for mobile. Screen recording. Likewise, I am doing the screen recording now. And for that, I am using one app, that's OBS. Its symbol you can find here. This, are you finding here? Your recording is going on. Is it clear?
Yes, sir.
Okay, no, it is just for additional information. You should know, therefore I discuss. Okay, fine. Here, class A kinds of metal, when they remain, then they prefer ionic bonding. And in such cases, especially basic strength matters a lot. Higher the basic strength, more the stability. And few examples for the donor atoms and the ligands that I discuss here. Is this first point clear? Yes, last time only one was replied. Now I want more replies.
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
Yeah. Okay. Now, second point
Yes, sir.
is covalent bonding. Covalent bonding, of course, due to both metal and the ligand, but here ligand role we are considering. Nepheloxitic effect you might have studied. Their cloud expansion. Covalent characters do remain. That conclusion we have sought out. Therefore, we went to the molecular orbital theory. So, to what extent that covalent bonding is there, and what is the main thing with whom that covalent bonding is there? That whom question is very important. Whether it is a class A kind of metal or it is a class B kinds of metal. Yes, will anybody help me? Which kinds of metal matters this covalent bonding? Which kind of metals want covalent bonding? Yesterday's discussion. Yesterday means last discussion. Day before yesterday lecture was there. That discussion. Class A or class B? Which kinds of metal from covalent bonding prefer covalent bonding?
Class A.
Class A. What's the other answer? Class A. Is it right? No, means you have not studied. Class A is a wrong answer. Class B kind of metal prefers the covalent bonding. For that, ligands also should equally respond. Less electronegativity should be there. Cloud expansion more should be there. Then covalent bonding will be possible. And class B kinds of metals will form the stable covalent bonding. So it's not a game of one-sided. That's the only metal ion. Ligands also are equally responsible. And in that ligand, who are less electronegative, who can expand cloud to more extent, cloud expansion, nepheloxitic effect to more extent, such ligands will prefer covalent bonding and will form stable complexes with class B kinds of the metals. So last time view was from metal point of view. Now the view is from ligand point of view. Let me make this concept clear by giving one example. Silver can form complex with chloride, can form complex with bromide, can form complex with iodide. Actually, coordination number is 2, so I represent that complex ion in this format. AgBr2 minus, AgCl2 minus. So these are the complexes of different halides. Here is a chloride, here is a bromide, and here is a iodide. Everybody's electronegativity is different. As per your knowledge, who is less electronegative among these? Chlorine, bromine, iodine. Less electronegative. Iodine or iodide is less electronegative. Who is larger? Ligand I am talking about. Chloride, bromide, iodide.
Chloride.
See, as we move from top to bottom, size increases or decreases. I had represent here size. It's the size of chloride, size of bromide, size of iodide. Who is larger? At least this basic you should know. You have to work for that. Otherwise, you are mechanically studying. I told to you, as we move from top to bottom, size increases. So where is chloride, where is bromide, where is iodide? At least that idea you should be with, no? So who is larger? Yes, I want answer from you now. Hint I had given to you. As we move from top to down along a group, size increases.
Iodide.
Yes, iodide is larger. Less electronegativity. It can prefer covalent bonding. Larger the anion is, larger the ligand is, what can it do? Will it prefer covalent bonding? Absolutely yes. On the ground of what? Nepheloxitic effect. Have you studied this nepheloxitic effect? Yes or no? See, how many are here? Why are you not replying? Yes, Ankita, Poonam, Vaishnavi, Rupashri and Alia. Is my question clear?
Yes, sir. No, sir.
Yes and no. Both answers are there. Have you heard nepheloxitic phenomenon or effect? That's my question. What is your answer?
Yes, sir.
Rupashri has answered.
Sir.
What is the answer of Alia?
Yes, sir.
Vaishnavi, Poonam, Ankita. See students, sincerity I want. If you do not attend lecture, I have no objection. Only assignments you have to complete. But if you are here, I expect that you have to answer. And certainly live sessions will help you. You are involving in answering. In syllabus also it is mentioned clearly in unit number 1. It is one of the evidence for covalent character in the complexes or coordination compounds. Ankit, are you there?
Yes, sir.
What's the answer?
Yes, sir. Yes.
What you did? Why for yes? What was the question? Yes, Ankita, what was the question? Vaishnavi, what is the question?
Nephrocytic effect.
Have you studied that? Have you heard name at least?
Yes, sir.
Study is different. Yes, what happened, Vaishnavi? Yes or no?
Yes.
Yes, okay. So this nepheloxetic effect deals with cloud expansion. That size increases. Cloud expansion more possible. So from ligand point of view, iodide is most suitable to form complex, to form coordination compound. And if you think about the metal, silver ion, silver ion, silver ion, all where same metal ion is present. Differences are in the ligands. And it is found that iodide is the suitable ligand for interaction with the silver. Why? Because, answer for my question, that silver belongs to which class? Class A or class B? Silver ion belongs to which class? Last lecture it is. Silver belongs to? No. Are you there? No. It is a class B kind of the metal. Class B. So class B will prefer, see the last video you will understand, prefer covalent bonding. So from mind or from the interest of silver, covalent bonding is necessary. And from viewpoint of these ligands, iodide is most suitable because it has less electronegativity, because it is larger in size, and therefore this Ag2 minus complex will be the most stable than AgBr2, which is most stable than AgCl2 is most stable, which is most stable. This conclusion is because of bond between them is covalent, silver is class B, and iodide is larger in size compared to others. Therefore, we can explain the stability. Wherefore, I am discussing this. Actually, last year you have not done those many experiments, but in organic chemistry, while determination of hydrogen, determining hydrogen, halogen, not hydrogen, halogen or halide ion by Lasagne's test, sodium fusion test. What you were doing, you are taking the sodium, you are fusing that, you are adding compound, then your reaction at fusion temperature. So that sodium ion will form and your halogen will get converted to the halide ion. So if there remain a chloride, it will form NaCl minus. If there remain a bromide, it will form NaBr. Actually not NaCl minus, NaCl, your NaBr and NaI. So what we were doing, we were maintaining the acidic condition because silver can precipitate in the basic condition, therefore acidic condition, and that silver ion were reacting with the halide ions and we were getting the precipitate. If we get a white precipitate, we were saying chloride. If we get off yellow precipitate, we were saying bromide. If we get thick yellow precipitate, we were saying it is iodide. If you have not performed into sense, then you have to listen at least. That such kind of variation coloration. But only coloration was not fair to distinguish. Chemical is necessary for the distinguishing purpose. So what was the reaction? In this any of the precipitate, add chlorine water. So what chlorine water will do? Chlorine water will oxidize this. And for that we maintain acidic condition also to break the complex, and chlorine water oxidizes and their complex breaks. And whichever ions are there, just give me one example. Here which ion is there? Ligand. Which ligand is there?
Iodine.
Charge?
-1.
I minus. It undergoes oxidation. Because of what? Because of chlorine water. And that I minus get converts to I. When will it be possible? By loss of electron or by gain of electron? I minus is equal to I plus. What should be there? Where will the electron? Left side, right side. Electron carries minus charge. -1 is equal to 0 minus or 0 plus. What should be there here? -1 is equal to 0 plus. What should be here in this bracket? Could you understand this? -1 is equal to 0 plus. What should be here in this bracket?
+1.
Suppose you take +1, 0 plus +1, 1. But the left side -1 is there, no? So what should be there?
-1.
Right, -1. That is the equation here. Here I minus -1. I 0 plus for minus charge. What should be here? Who carries negative charge?
Negative charge.
Who carries negative charge? What is this? E means what? E for what?
Electron.
Right, electron which carries negative charge. So here electron is lost. Electron is given out. and therefore we can say it is an oxidation reaction. And who is oxidizing agent? This chlorine water is oxidizing agent, and that will oxidize iodide to I. But alone I can't remain, is unstable. As like alone hydrogen can't remain, it is unstable. Alone oxygen can't remain, it is unstable. Alone chlorine can't remain, it is unstable. Likewise, alone I will not remain, is unstable. So what will happen? I plus was a stable form of iodine, stable form of nitrogen, stable form of oxygen, stable form of hydrogen. How we represent hydrogen? How it remains generally? Okay, I plus I. What will be there? At least complete.
I2.
I2, yes, I2, gaseous iodine. Actually, that iodine at room temperature can be solid, but is a molecular iodine. So, iodine in molecular form can be obtained from nascent iodine. Nascent iodine will combine with other nascent iodine to get the molecular iodine. Are you understanding what I am saying?
Yes, sir.
Yes. So this iodine can be identified because iodine in water or aqueous medium shows yellow coloration. Or if it comes in the CCl4 layer, organic layer, CCl4 or chloroform layer, iodine shows purple color. Bromine shows yellow color and chlorine shows no color. That's a distinguishing test for halogens. Means what is happening here? When we add chlorine water is oxidizing agent, and in case if any precipitate of halide ion remain, say that's a precipitate of silver iodide, that iodide will get converted to iodine. Bromide, silver bromide will get converted to bromine molecule. Chloride gets converted to the chlorine molecule. But those are with different colors. I said iodine shows what the yellowish color, dark yellow color. Bromine will show the pale yellow color, or chlorine will show the no color. But in aqueous medium, not easily recognizable. So we use the organic medium. We add a few drops of chloroform or carbon tetrachloride, and if we get purple color, then certainly iodine is there. If we get yellow color, then bromide is there. If I get no color, then chloride was there. Likewise, we can what? Conclude. But here, suppose chloride also is there and iodide also is there. In such cases, who will precipitate? Means what is the question? Silver ions are there in the solution, or we are adding those silver ions. And by the way, there are iodide ions as well as there are chloride ions. Who will combine with silver ion first? sorry. Who will combine with silver ion? Iodide or chloride? It depends upon kind of interaction. It depends upon nature of metal ion. It depends upon nature of ligand. About nature of metal ion, if I have to talk, just already you have answered. Again, answer please. Silver ion, what type of metal it is? Class A or class B?
B.
Class B. So it will prefer which kind of bonding? Covalent or ionic?
Covalent.
Covalent. Among these ligands, iodide and chloride, who will prefer covalent bonding? That ion which is larger in size. That ion which is less electronegative. That will prefer covalent bonding. So who will prefer covalent bonding?
Iodine.
Iodide will prefer covalent bonding. So silver will tend to combine with whom? The silver ions are there. Those will tend to combine with whom? Silver ion will combine with iodide or chloride. Silver wants covalent bonding. Iodide can prefer covalent bonding. So with whom it will combine?
Iodide.
Iodide. Yes, iodide. So this silver will combine with iodide. This silver will combine with iodide. So chloride ions will not be there. But by any means, if there is silver chloride, says AgCl2 minus formation, and outside of this complex ion, there are iodide ions. In such cases, see how interesting thing it is. Silver ions are inside. Chloride ions are covering that silver ion. Out of this bracket, out of this complex ion, iodide ions are there. But iodide ion could sense a silver ion. It is their ability, power. Silver ion could sense iodide ion outside. In terms of silver, just think what silver will think. Already I have friend. That friend is Cl minus. And I can obtain friendship. I can form a bond with one more ligand. That's iodide. So one more friend is waiting outside. What silver wants? Silver wants good friendship. Then silver thinks, who can be the good friend of mine? Then silver feels that in spite of chloride, iodide. So it will do such a thing by which this bond will break and iodide will come inside. By the way, iodide also will think, iodide will come to Cl minus and will say Cl minus, see, I have the great affinity with silver ion rather than you. So it is my role to obtain the friendship with Ag plus, silver ion. Get out from here. So iodide also will remove this Cl minus, Cl minus, and will form a bond. So what will happen? These chlorides are there, those will get removed and new complex will form, that is AgI2 minus. Is this discussion clear?
Yes, sir. Yes.
Yeah. Similarly, suppose if I consider AgCl2 minus, it as a complex, and outside there are bromide ions. Same story. Silver will think, now I have the friend chloride, but by the way, one more friend is there, bromide. What shall I do? Shall I continue this bonding or shall I break this bonding and go to the bromide? Answer for silver. Silver will think about the bromide. Silver is thinking bromide. By the same way, bromide finds that silver is forming friendship or doing friendship with poor chloride, and that bromide will say to chloride, get out from here, it's a bossing, and that chloride has to go out. So bromide is dreaming to form bond with the silver ion. So both dreams, dream of silver to form bond with bromide, dream of bromide to form a bond with silver, will result a cleavage of this bond, breaking of this bond, and new complex will form, and that complex is AgBr2 minus. Is it clear?
Yes, sir.
Yes, sir.
Likewise, I need your help now. If I consider AgI2 minus and outside there are two Cl minus, what will happen? Will there be any change in the complex sign? I2 minus, or iodo complex will change to chloro complex? Students, are you following what I am asking?
Yes.
What will happen? Okay, logic simple, you have to apply. Silver ion is with bond I minus. One more friend is there, that's a chloride minus. Silver ion will form strong bond with iodide or chloride. Silver ion is a class B kind of iodide. So it will not dream for chloride. It will not at all. It will not think about chloride because iodide is strong ligand for that silver now. Iodide is a good friend for the silver. Good covalent characteristic, good understanding between them is there. Similarly, chloride, even if it comes, chloride will find I can form a bond with silver, but already boss is there. Already big ions are there. Great bonded ions are there. So chloride can't do anything. But if chloride remains inside, iodide will be changed. It happens in the chemistry. Means in society also we find somebody comes over there, can replace somebody or respect as such. So iodide has not to respect this chloride. Already chloride will remain outside. So whenever by any means if chloride forms and if newly iodide ion comes or bromide ions iodide or bromide ions do come, then chloride has to go out, bromide iodide will come in. So that's a displacement will be there, and that stability of iodo complex can be explained by covalent characteristic or covalent bonding between metal ion, silver ion and ligands, that's I minus, which are larger in nature. So it is a covalent bonding point. I sum up this point. Covalent bonding is a favorite bonding for class B kinds of metals. But my point of interest here is the ligands. So ligands which are less electronegative, ligands which are larger will form strong covalent bond. So class B kind of metal, say example silver ion, and around that if options are available I minus, Br minus and Cl minus, then silver will prefer iodide, secondly bromide and lastly chloride. It's the conclusion of this point. Is this point clear?
Yes, sir.
Yeah. The next point is there, that's a concentration. Let me complete that point and we will conclude today's lecture. Not only the category of the ligand, but concentration of the ligand also matters. Interesting phenomenon it is. Just for example, cobalt thiocyanato complex SCN4 2 minus. It's a blue in color, and in that suppose if I add water, it will form complex COH2O6. What should be charge? Which metal line is there? Here, charge on the metal line. It's a 2 plus and its color is pink. Plus that thiocyanate ions are there. Those are displaced. Here two ligands are there. One ligand is thiocyanate. Other ligand is aqua or water. Cobalt has tendency to form bond with both. But when sufficient concentration of thiocyanate ion remain, then this blue colored complex will be there. But if you add water in that, then net concentration of ligand, metals will change, but my point of view is ligand. Net concentration of ligand will decrease, or concentration of the water or that ligand, abundance of the ligand will increase. Actually, decrease is here, so indirectly we are feeling as increase, but water, there's no more change in the concentration. But concentration of thiocyanate is decreasing, then what happens? The bonding with water starts. And how many water molecules do surround? 6 water molecules do surround. And what's the color of that octahedral cobalt aqua complex? Is a pink in color. So only after dilution color will change. Generally color defades, but here color changes, and color change is due to change in concentration. Conclusion: sufficient concentration of ligand is necessary to obtain a suitable stable complex. If that concentration changes, new complex may form. Here in this example, water was a ligand added. Dilution I did there. Concentration of thiocyanate decreases. Complex changes from thiocyanate to aqua. Is this one example clear?
Yes, sir.
Yes, at least one more reply.
Yes, sir.
Yes. Now, second example that I am giving again the reddish brown color. F.E.S.C.N6 minus 3 plus 6F minus, that results one complex. It is Fe.F6 minus 3. Of course, the thiocyanate ions will what? Come out. And how many? 6. Red colored thiocyanate complex changes to colorless fluoro complex because concentration of ligand is changing. Here who was dominating? Thiocyanate was dominating. Here who is dominating? Fluoro is dominating. Why? Because we have added the fluoride ligand. So by adding a new ligand, by increasing concentration, other complex can form, or decreasing concentration of previously ligand, bonded ligand, the change in the complex will occur. Complex changes, color will change. So it's the second example. One more example that I give it to you. It's a copper aqua complex. Means water is there as a ligand, and color of this complex is blue. In this, if I add say chloride, it's from tetrahedral complex there later. It gives yellow colored copper chloro complex plus 6H2 will be there. Coordination number also changes by the change in the ligand. My point of view is not a coordination number. My point of view is the strength of the ligand or concentration. If concentration of chloride, actually Cl minus should be there, chloride increases, yellow colored copper chloro complex will form there. So students, I had told you 3 examples. What was the first example? Which complex was there? Yes, cobalt.
Thiocyanate.
Right, cobalt thiocyanate. See the number of ligands there. How many ligands were there? That color was blue. 4 ligands. Color was blue. And after adding water, it has changed to cobalt aqua. 6 water ligands. And color was pink. Yes. Are you following what I am saying?
Yes, sir.
Second example was Fe. Yes. Which ligand was there? Fe. Yes. Which ligand was there at the beginning? Red color complex it was. It was F.E.S.C. and thiocyanate 6 minus 3, and which is converted to colorless complex. That's a Fe.F6 minus 3. Now at least answer third example. That's a copper complex. Yes. Which copper complex was there? Cu. See, blue color was there. Aqua complex. COH2O6 plus 2. Now at least this you answer. Which was yellow in color?
Cl4.
Cu.
Cl4.
Cl4.
Cl4 minus 2. Okay. So conclusion: thiocyanate concentration decreases or water concentration increases, pink color. Blue converts to pink. Thiocyanate concentration decreases. Fluoro concentration, not water. Fluoro concentration increases, colorless iron complex. Water concentration decreases, other than what you can say, chloride concentration increases. A chloro complex will form. So it's a basis of understanding of thermodynamic stability. So nature of coordinating groups that we are discussing. The first point was their strength, Lewis strength, basicity, basic strength. Second point was, first point related to ionic bonding. Second point was related to covalent bonding. And third point was related to concentration. So these 3 points I discussed today regarding the nature of ligand. Are these 3 points clear?
Yes, sir.
Okay, students. So next time we will discuss the third main factor. That's the presence of rings or chillet effect. If any doubt is there, be free to ask. Otherwise, we can stop. Shall we stop now? Okay, Rishikesh said no doubt. Okay then students, next time we'll discuss the next point. That's the presence of rings and its effect on the thermodynamic stability. I declare here today's session is over. Quit now.